Yeah, so today we're gonna continue our conversation about renormalized perturbation theory. We're gonna be discussing QED in more detail. In particular, there will be two diagrams. We discuss vacuum polarization and how the renormalization condition for vacuum polarization at one loop in QED. Today we're gonna talk about the other two diagrams. I did not understand what's going on. So what are the two other diagrams? The fermion, um, the fermion mass correction, and then which at one loop. What is the diagram that contributes to it? So this one, and then the other one is the vertex correction. That at one loop, there's really only one diagram. And it's this one. So we're going to talk about these two. This is the more complicated diagram. And I'll go over it a little bit quick because we're going to come back and do similar calculations for non-abelian gauge theory. All right, so very quickly reviewing what the philosophy in renormalized perturbation theory was. We take the bare Lagrangian with bare parameters, introduce a renormalized Lagrangian with renormalized fields and renormalized couplings. Then the difference we are going to call counter terms. Of course, all the renormalized fields and couplings, we haven't set them yet. So if we know the left-hand side, the bare parameters, the difference between the two goes into counter terms. So fixing what the renormalized values are is equivalent to fixing what the parameters and the counter term are. Counter terms are. So these parameters are these deltas that we talked about. So how do we fix that? Using experiments. That's the answer. So these are called renormalization conditions. They're conditions that we set on the renormalized perturbation theory, or renormalized quantities from experiments performed at a certain energy scale. For example, we go and perform an experiment and see at some energy scale q squared over equal mr squared, right? Some value of mr squared. The 2-point function shows a pole, right? There's a pole. That is a physical mass of the particle, right? So we set this condition at one loop in our theory that will fix for us the parameters and the counter terms. And then we say we have renormalized the theory at one loop at a particular scale. Then once you normalize the theory at a certain scale, you have fixed all these parameters, then go and calculate whatever you want, right? Because those parameters are set. All right, any questions about this philosophy? We talked about, so there were three types of, from superficial dimension counting, there were three types of theories we talked about. There were the renormalizable, super renormalizable ones. What's the definition of super renormalizable theory? Only a finite number of amplitudes diverge, right? These are super renormalizable theories. They carry in lower dimension, in particular in 2 dimensions, often 1 + 1. Then we have the renormalizable theories. These are the theories where a finite number of amplitudes diverge, right? But there could be infinite number of diagrams. So for example, in QED or all these theories, these are renormalizable theories. So as you go to higher and higher orders, there are new diagrams that diverge. But that's okay, because with a finite number of counter terms, you could capture all the divergences, right? Then there are the non-renormalizable theories. These are theories where basically as you go to higher and higher orders in perturbation theory, you need more and more. There are brand new infinities that appear. You need more and more parameters, and you will never be able to capture the full theory, the full non-perturbative theory, with a finite number of couplings. However, as a perturbative theory, as an effective field theory, these are perfectly fine theories. And one has to say that we're going to talk about what is the role of effective field theory. Effective field theories are extremely powerful and useful. Like you might not know much about it, but a lot of EFTs that we write down and play with that describe the nature around us are actually not necessarily normalized. Now you're going to see later on that, and that the principles of quantum field theory, we said it, at the very beginning of the course, which were symmetry, locality, and separation of scales, they apply here, right? So these are principles of EFT as we learned from Landau. But we'll see that actually this is a little bit more complicated. There could be non-localities, blah, blah, blah. All right. So we're talking about QED today. And as I said, we're going to be focused on these two diagrams, fermion self-energy and vertex correction. So let's start with the fermion self-energy. We did these integrals in the at the end of the QFT1, but I'll repeat them very, very quickly to just so that you first remember all those integrals. It was the end of the semester. So here's a fermion propagator. Of course, you could write it as a in terms of the 1pi propagator, right? So this way you resum it, right? The 1pi, what was the definition of 1pi? It's the sum of all diagrams that if you cut any line, it will not be disconnected, right? So here's the propagator for the 1pi, propagator. This is the full propagator that could be written as I over P / minus M sigma of P, and the sigma of P is the 1pi amputated 2-point function. Good. Now, notice that this sigma is not, this is a function of P. That means that not only the sigma can shift the pole, but it could also change the residue. Right? So if there's a term that's linear in P, that will change the residue. Right? That was important. We saw that for the in the case of the vacuum polarization. So you expect two conditions. One of them would be on the value of the 1pi amputated diagram, if and then the other one would be on the first derivative in the case of fermion. In the case of a photon, it would be on the second derivative, because in the case of photon, the propagator would be P squared. In the case of fermions, notice that the sigma of P is a matrix with spin indices. This is something that you should always remember. This shorthand notation, these are matrices, right? This P slash is P mu gamma mu, and gamma mu is a 4x4 matrix in 3+1 dimensions, right? And even though we write M, what we mean is M times identity. Good. So basically, well, think about it this way. This is the 2-point function, the time ordered 2-point function of psi and psi bar, which is going to be I Z2. Z2 is the field, the renormalization, right? So renormalization of the fermion field, and then over P / minus M, this is the residue, right? So we're going to focus on this diagram. Is the calculation clear? So to be very clear, the sigma P slash is going to be a function of P slash, right? Hopefully you can argue for that. It cannot, yeah. Sigma P slash at P slash equal MR, the physical mass, whatever it may be, this sigma should be 0. And the first derivative should also be 0 to make sure that the residue is 0. So this is by setting these conditions, well, we're going to calculate sigma P slash equal MR at sigma at P slash equal MR, and this is the answer. Well, we did this calculation last semester at the end of the semester, but I'm going to repeat it very quickly. What does it look like? It looks like the alpha QED, which is E squared over 2pi, MR, normalized mass, over 4pi. This gamma of epsilon over 2, this should be familiar. We saw that in the vacuum polarization on Tuesday as well. This 4 pi mu squared over mr squared is also familiar. This is where it comes from, if you recall. It's actually the structure of it. In the case of vacuum polarization, it was this expression, 4 pi mu squared to the power of epsilon minus epsilon. Let's get the over delta, right? Then this delta was m squared minus x minus, actually it was something else. That's what it was.
Square. 2x.
No. Well, okay, you go back and look at it. But what matters is that this delta at q squared f equal mr squared is what we have down there. All right, and then these epsilons are the epsilon expansion, space-time dimension being 4 minus epsilon. Good. So if this is the answer, you have to add to it this diagram, the counter term, delta of m, and the result should be 0. That's one condition. That will set for you delta of m, which is minus of this. And then the other condition, we're going to calculate the sigma. Here I immediately put p slash equal mr, but you take a derivative and then put p slash equal mr. And here's the answer you get. Now, this should be compared with delta 2. And once you compare it, it will set the delta 2 to be something like this. Now, I'm going to repeat this. You might be wondering, what the hell is this C parameter? And we're going to go over that. I discussed this last semester, right? The arc C gauge. All right. For those, yeah.
Sorry, the delta 2. Why does it appear in the derivative?
No, the delta 2, so. Where is it? I'll go over it. It's not appearing in the derivative. You calculate, where is it? Yeah. You calculate sigma. This sigma that you calculate will just give you this answer. Right? Now you should have in the Renormalized perturbation theory, you have these counter terms. And you have to add to them, and delta 2 is the right term that's just next to it. It has to cancel it. I'll go over it. But let me just remind you what XC is. Does anyone remember what XC is? I'm pretty sure I introduced it at the end of last semester. It's an arbitrary gauge. It's the arc C gauge. We're gonna go over it. But keep this in mind that, well, okay, let me repeat the calculation very quickly. So what am I calculating? I'm calculating the following diagram. So I'm calculating, no, not that. This is the diagram I'm calculating, right? So there is a loop. So there is a k integral that I have to do, right? There are 2 vertices. Each of the vertices will give you minus IE parameter. One of them will give you gamma mu. The other one will give you gamma nu. The mu nu indices are going to be contracted with the photon propagator. So there's a fermion propagating here. I've written the amputated diagram. So that's the only thing that matters. Right? So from this, you could see that my variables are k is running like this. And then this is q minus k, and q is the incoming. Good? Is this expression clear? And here's a photon propagator. I'll put it on 1 over q squared. So this arc C gauge is the story that we're going to see in a second. I'm going to review it. That what sits here is actually C minus 1. This propagator we've written down. We did this actually in absolute detail last time. This corresponds to a particular choice of gauge, which corresponds to C equal to 0. There are other choices of gauge. C equal 1 is when this is 0. That has a name. In that gauge, the propagator photon is proportional to eta mu nu. What did we call that gauge? Feynman gauge. it turns out that when you do these diagrams, you're gonna see what's gonna happen. So actually, let me tell you in advance why this is important. If you calculate, we're gonna see in a second, I'm gonna show you the calculation. If you calculate this diagram, and we're gonna do the calculation pretending that the photon propagator is just this. Over q squared. Then you will see that this diagram actually does not diverge, right? You see that it does not diverge, and that is a little weird. It turns out that this diagram is actually, when you do the integrals, there are parts of it that are gauge dependent. So you have to be very, very careful. It's the way to be careful in perturbation theory of gauge theories is to work in the RC gauge. So you explicitly keep the case of the choice of gauge explicitly to just keep track of what terms are physical and what terms are not physical. And then in the case of non-abelian gauge theories, we're gonna do a really cool trick. We're gonna integrate over choice of gauge. Good. So what should be sitting here is actually C minus 1. But I'm gonna wait a second. Do I need to? Wait, I thought I had slides about RC gauge. Where are my slides about RC gauge? I can do it on the board, but I don't remember where the slides RC gauge are. But we're gonna come back to it. So let's just work in the gauge, which is C equals 0 for now, for this diagram. Okay, so let's focus on this bit, because that's the only thing that matters, right? What does this look like? Well, this SF will have 1 over Q slash minus K slash. The way we usually write it is 1 over K minus Q squared minus MR squared minus M squared, and then write down this part on top, right? So hopefully you remember this. Right, which we write as what have I done? This was an inverse matrix. I just inverted it so that I deal with like a simple coefficient, and I contract in this, I deal with matrices in the numerator. That's easier, right? That's exactly why we deal with Feynman parameters. All right, so then when you do that, of course, there will be 1 over K squared squared coming from, what is the K squared squared? Because I've taken, so this guy, I've taken this K squared out. So that's why I get K squared squared, right? And then 1 over K minus Q squared minus M squared, this parameter. Good. So how do we deal with these diagrams? First, let's just do our index contractions. Let's do just the gamma matrix business. This is what it looks like. You could massage it into 2 terms, this term and this term. We're gonna deal with these. You might wonder at this point, why am I splitting them this way? You'll see actually, the way it works is the following. So this term has an explicit K squared in front of it. This one does not. So what I'm calling term 1 and 2, their difference is in the following. Term 1 looks like something over K squared, K minus Q squared, integral of d4 of K. So if I want to introduce a Feynman parameter here, the Feynman parameter would be 1 over AB. The other one doesn't have a K squared down there, over there, so it's like this. And I have to introduce Feynman parameters for 1 over A squared B. That's why I'm separating the 2 terms. So let's do the first one. This is the 1 over AB. you get this. When it's 1 over AB, there's only one parameter, x, that you introduce. And this is what it looks like. Then the rest of it is pretty familiar. You first introduce k mu minus x q mu as a new variable. This is what it looks like. You do Wick rotation. This is your expression. Now that you've done Wick rotation, you have managed to turn this integral into just this. Now you could perform this integral. It's a bunch of gamma functions. And this is what it looks like. We're not going to do the x integral. It doesn't matter at this point. This is the expression we have. And the next step would be expanding. This near. So here in this notation, these three space dimensions. Sorry. So in d plus 1 equal 4 minus epsilon, you expand this. You're going to get an expression like this. And then we've already talked about minimal subtraction and the MS bar scheme. Right? So this is how this integral is done. At least term 1. We just discussed term 1. Now, we have to consider the contribution of term 2. As I said a little bit earlier, this term 2 has 1 over k squared over this guy. So we have to deal with 1 over a squared b. We have to introduce a Feynman parameterization for this. This involved two integrals of dx dy. This is just an identity. So you massage it. We discussed this last time, last year as well, actually. And this is the expression you end up with. As before, you introduce a new variables. You see the set of tricks we have are always the same. It's lengthy, but they repeat. You introduce a new so when you have an integral, you first write everything. If you have fermions in terms of denominators that are whatever they are, and then bring all the matrices in the numerator. Then you look at you organize your numerators so in such a way that you can actually see what is the denominator, what is the 1 over a, what is the Feynman parameterization you need. You try to do the minimal Feynman parameterization, right? You try to do that, and sometimes you can't do better, so that's why here you're doing 1 over a squared b. You do the Feynman parameters, you define new variables so that you're dealing with a rather straightforward integral like this that you could perform in after Wick rotation, and the results is in terms of gamma function and a bunch of parallels. Okay, so Wick rotation, you expand in 4 minus epsilon dimension, MS bar scheme, you obtain the answer. So this is the answer for the second term. And I have kept the Q dependence in there, right? Why am I keeping the Q dependence? Because the renormalization conditions had two parts. One is you first set Q equal MR squared. The second one is take derivative with respect to Q and then set it. That's why I'm keeping the Q dependence. All right. Combining in terms 1 and 2, we find that the total divergence looks like the following. So this is what it looks like. This is an MS bar scheme. 3m alpha over 2 pi, 1 over epsilon bar, plus alpha m over 4 pi, this guy. So pull of the propagator in the particle mass has to satisfy this, right? And you could set it, and you get the results that I discussed earlier. Is the idea clear? I understand that I'm going through this really fast, but these are calculations that are rather standard. You have to do them, and you will do them in your homework. Maybe you have already dealt with them. But are the steps at least clear? I know that I'm jumping over a lot of algebra, but that's just the nature of these calculations. I can't reproduce every step of it on the board. I mean, it takes time. Yeah.
The minimal subtraction scheme is not the only scheme there is.
Of course not.
And how do you solve that freedom?
Oh, it's convention.
It's convention.
It's just convention.
But when I want to plug in numbers that I will measure in nature, how do I fix? How do I?
Does anyone have any answer? So when you calculate things, your final answer of the renormalized theory will not have any epsilons in it.
No matter how many terms I subtract.
Of course not. It's renormalizable, right? I think is the principle clear? What the idea of the counter terms is to capture these epsilon divergent terms. So if the counter terms cannot capture 1 over epsilon terms, 1 over epsilon bar terms, doesn't matter. If they cannot capture them, you haven't renormalized, right? So what you're asking is, I understand what you're asking. It's a tricky question. You're asking the following question: if it doesn't matter which scheme do we use, why do we give this a name? Right? Why even talk about 1 over epsilon, defining 1 over epsilon bar? Now that's a very tricky question, and it has to do with something we haven't discussed quite yet. It turns out that as we go to higher orders in perturbation theory, some physics we're interested in ends up being scheme dependent. At first order in perturbation theory, no big deal. Everything is going to go through. It's all nice. We're going to see examples of this. I have not interpreted this for you guys, what it means to have scheme dependence in perturbation theory and quantum field theory, right? But we're going to get there, and that's going to be about renormalization theory. At this level, it doesn't really matter. We haven't encountered a situation where the gauge, sorry, not the gauge, the choice of regularization or scheme matters. Any other questions? So there is a little bit of a lie I've told you so far. At the first order in perturbation theory, it hasn't come up yet, but that's why we have the renormalization theory. We're gonna discuss that. The lie is that I've told you everything is gonna be epsilon independent. So here's a fix of it. The correlators, right? All observables are gonna be epsilon independent, but couplings or values of the field are not observables. So they will depend on epsilon and harder in perturbation theory. However, anything physical will come out epsilon independent. Well, it's a tricky, loaded question. We need the full power of normalization theory to discuss that. Good. Any other questions? Why do we need something like 1 over m sparse scheme? Because, well, some of you guys who are experimentalists might have seen this when people publish data like about couplings and stuff. The couplings could be coupling dependent, scheme dependent, and they actually have to tell you what is the scheme. So this is just a convention that most people use them as sparse scheme. All right, vertex correction. Any other questions? Let me make a pause. I think I don't want you guys to get lost in complexities of this. By the way, do you guys remember what sigma 2 was, or do I need to? Delta 2 was? Why did I add delta 2? Delta 2, what are the counter terms? I think I forgot to say that. So the delta 2 is this counter term. Right? So it's pretty clear why I was adding this to this diagram. Right? All right. So now the vertex correction. The vertex correction is this thing. Well, the correction at one loop is this, and then there is a counter term that you will have to deal with. This is the counter term to deal with. It's called delta 1. Now, we talked about word identities in QED last time, and then we said word identities in QED relate this guy to the fermion mass renormalization, right? If you remember, we wrote down the full propagator in terms of the propagators of the P and P prime, and then we said, well, if P is the incoming and P prime is the outgoing, Q is the P minus P prime is the photon that's being emitted. If the photon is very, very low energy, right? Photon is massless, so it could be arbitrarily low energy. Then you could expand P minus P prime, and you could expand around 0, P equal P prime, right? So at exactly 0, at 3 level, you just get the vertex you expect. But at higher orders in perturbation theory, you'll find relations between the renormalization of the fermion propagator, fermion propagator, and the vertex correction, renormalized vertex. And basically, the observation was that we'll see that delta 1 has to be equal to delta 2. As a result of the word identities. Here's the explicit relation. This is the fermion mass correction. This is the 1 pi amputated fermion propagator, and here's the vertex. Check this from last time. Question? So if I know this relation, I actually don't need to work very hard. But I'm gonna calculate this one loop diagram for you in a very, very brute force way to try to make a point. This diagram has all sorts of complexities in it. All right? You will have to fill in because the calculation is very, very involved. It's more involved than the other two. So of course I'll jump over algebra steps, but you will fill them in. Good? So for the remainder of this lecture, this is my plan. My plan is to go over this guy. We're going to discuss various aspects of this. And then we're going to end on some comments on higher order perturbation theory. Yeah, forget about that. Okay. Vertex correction at one loop. So K1 comes. Sorry, I keep switching between K and Q. That's just life. So K1 comes and K2 goes. There's some photon that's emitted, and then there's some sort of P that propagates this way. So I'm integrating. The loop integral is P, and I'm calling this lambda mu, capital lambda. This is the value of this integral. All right. So what does this look like? Of course, it will be only a function of K1 and K2, right? Because the conservation law will tell you that whatever this photon is, it has momentum K1 minus K2. K2 minus K1, but whatever. K1 minus K2. All right, so there are 3 vertices. Here are the 3 vertices, minus IE3. So the first indication that this diagram is more complicated is that there are 3 gamma matrices. And there is a fermion propagator here. There's a fermion propagator here. So this is K2 minus P is this fermion propagator. K1 minus P is this fermion propagator. And then there's a photon propagator here that I'm going to write down in arc C gauge. Good. Here are these space dimensions. So let's first do a power counting. And why is this parameter there? In anticipation for dimreg. Well, not anticipation. I already wrote this in D+1. So that's required by dimension counting. Good. All right, so this is lambda to the power 4 divergent. This lambda is not this lambda, so not get them confused. This is if I had the sharp momentum cutoff lambda, this would be lambda 4 in 4 space-time dimensions. This is 1 over lambda. This guy is 1 over lambda, and this is 1 over lambda 2. So what's the divergence like? Log divergent. So that's good. This divergence is independent of K1 and K2. Why? Can you see why? It's just a simple dimension counting. Can you see why it cannot depend on me? So look at the divergence structure, right? The delta, the photon propagator does not have K dependence. So that's it. The K dependence only appears in the fermion propagators. But to pick the most divergent piece of it, you'll have to, when you look at K1 minus P, you'll have to take the piece that is P dependent. Otherwise, the other term is less divergent, right? So we're interested in the most divergent behavior of this. We're interested as K1 minus P is like, well, like 1 over K1 minus P squared. Yeah, something up here, right? Something up here. If you are interested in the most divergent behavior, oh, sorry, actually, I'm talking. No, actually, you fill this in. Why is it independent of it? Well, it's actually, I almost gave you the argument. But if you expand this whole expression in terms of the P dependence as a series expansion in P, the most divergent term will look like this. Okay, but we're gonna do this calculation explicitly. So as usual, the very first step is to deal with the Dirac algebra in the numerator. Let me see. Do I want to actually go through this? Yeah, let me skip this bit of it. What I was gonna say is, if you did not take this choice RQC gauge and just took the case of C equals 0 that we discussed before, you could show that you can calculate and you see that there is no divergence. You could perform the Dirac algebra in the numerator, do the calculation, and find an answer which is actually not divergent. But the point is that this is gauge dependent. We're gonna do the RQC gauge. We're gonna do the integrals properly and keep track of everything. So a comment about the RQC gauge. Let me do this on the board. So what is the RQC gauge? It's something that we use for gauge theories. The action was this, right? After doing a bunch of integration by parts, what you're gonna find is you're gonna find A mu, A the mu nu, del squared minus Q mu. Oh, sorry, what am I saying? Del mu, eta mu. Right? Is this clear what's going on? So F mu nu is del mu, A mu minus del mu, A mu. Right? And then previously what we did was we just inverted this. Good. Now, what we're gonna, oh, actually, let me not erase this. What we're gonna do is we're gonna add to this the following term in the Lagrange. Minus over del mu A mu squared. If you recall, this was a choice of gauge. right? We talked about Lorentz gauge, del mu a mu equals 0 gauge. So this is it. By adding this term to a Lagrangian, you're fixing a gauge. Now, what does that do? It will change this to C minus 1 a the mu, oh, sorry, del mu, del mu. If you invert this guy after Fourier transform in momentum space, what you find is that in arc C gauge, the propagator will look like Q squared a the mu nu. How do I want to write this? Actually, no, that's not what it looks like. A the mu nu. Let me see. 1 over C minus 1. Yeah. And then this one will be C minus 1. Yeah. Q mu. Q mu. 1 over C squared. Oh, yeah, that's correct. That's just Fourier transform inverting back. So C equals 0 is the Lorentz gauge. By looking at this action, can you see that C equals 0 is the Lorentz gauge? Can anyone argue for that? Why is that the Lorentz gauge? What are we gonna do with this Lagrangian density? We're gonna put it inside the path integral, right? Inside the path integral, we're gonna write e of a mu e to the power of this integral of this. Well, in this notation I've written, yeah, that's good. When C goes to 0, this path in this path integral, this term goes to infinity, right? So the configurations that have del mu a mu not 0 are infinitely suppressed, right? That's what it does.
But in the equation of motion, it doesn't make any sense, right? Because you have one where C explodes as well.
Does it make any sense or not? Think about that. That's a very good question. The answer is yes, it does make sense. You just have to be careful with your limit. We wrote down the equation of motion Lorentz gauge. If you go back and we wrote down all sorts of gauges, right? And equations of motion were pretty explicit. That's why it's important that when you see these things, don't buy them immediately. Go back to the old notes or wherever you found there these equations and convince yourself this is okay. Now, what we're gonna do is we're gonna do the calculation within the case that was C equals 0. I didn't go over it because of time. But if you do the calculation, you do the integrals every single step, you find there's no divergent term. But that is silly because if you do the calculation properly with the arc C gauge, you find this answer, which is C dependent. We're gonna do that. Also, something to remind you is that I went over this very fast. I didn't give you really a chance to ask a question about this, but where was it? Well, I'm not finding it. But anyway, there was a C dependence in the previous calculation as well, in the fermion propagator. Why did I make that comment? Because word identities tell you the divergence of this has to match the divergence of the other one. Right? They say delta 1 is equal to delta 2. So if delta 1, part of the calculation is gauge dependent, C dependent, the other one better have the same ambiguity or gauge dependence. That's why it's silly to fix the gauge. Well, it could hide some subtleties fixing a gauge, particular gauge, and try to do these calculations. All right. Back to the one loop vertex. So this is where we were. Now we're gonna take the photon propagator to be this thing, and we're gonna find the divergence structure to be of this form. What is the Feynman parameterization we need? Actually, I think I'm gonna go over it. Yeah, no, but let me just. Can you see the Feynman parameterization we need? The terms that are divergent, one of them has 1 over k squared here. I think p squared here. Sorry. This is p. So, whoops. There's a 1 over p squared here. There is 1 over k1 minus p squared coming from this term, because we're just going to separate the denominator, and 1 over k squared minus p squared, k2 minus p squared here. So what's the Feynman rule Feynman parameterization I need to use? 1 over ABC. This is the fanciest one. It involves 3 integrals, x, y, and z. That's why we're doing this last, right? So the vacuum polarization, the Feynman parameterization only involve 1 over AB. The fermion mass, fermion self-energy involved 2 terms. One of them was 1 over AB. The other one was 1 over A squared B. 1 over squared B had 2 variables. Here is 1 over ABC, so 3 variables. So it's a tricky one. We're going to see something very, very subtle happening. That's physical. That's why I want to walk you guys through this calculation. Of course, here, the change of variable has to be the one that makes sense so that you could perform your integral properly, right? So you define this variable. Oh, actually, So I'm already playing a trick. There is this gauge-dependent term. One way to separate the effect of the gauge dependence is a nice trick, is to do your calculation just to calculate this term, the not Xi-dependent term. You do that by setting Xi equal 1. So let's first set Xi equal 1, do the integral with this bit, and then we're going to take care of the Xi-dependent part. So the Xi equal 1 part is sort of straightforward. Here's what it looks like. This is your numerator that you have to do your Clifford algebra. There's integral over x, y, z. This is what it looks like. This is your Feynman parameterization. Integral over the loop. This is what it is, right? And wait a second. I think I have a typo here. Yeah, this should be I cubed. This should be 2 to the power of 3. There are 3, just by counting, right? There are 3 vertices. All right, so this is what you have upstairs. You have to use Clifford algebra, Gordon identities, all the identities you know about these Gauss matrices to calculate this. You massage it into this form. And in massaging it into this form, I've used these relations. Do you remember what, what's that called? Xi mu nu is? What was Xi mu nu? Yeah, we use Xi mu nu to build generators of the Poincare transformation. All right. So after you do these massages, one more thing. So let's call the term that is Xi equal 1 to be F1, capital F1. And then the other term I'm going to call F2 so that we separate them. So we're calculating F1 for now. So here's the F1 of Q squared. There is this integral and this whole thing. So I've written it. There's an integral over x as well that I've suppressed for now. It looks like an awful thing. You have to do your calculation, the set of tools that you have. You do your I've performed the integral in Euclidean space, and this is the answer you get. Then there is a okay. Actually, do I want to say it this way? Yeah, that's fine. This is the answer again. I'm gonna put the pieces back together. Now let's calculate the piece that has c minus 1. This one, if you actually do it properly, would require 1 over ABC squared. Sorry, I think what I said was incorrect. F2 is something else that I've defined. Yeah, okay. So it involves this Feynman parametrization. Again, you will have to do this calculation. You have to look at it to start the integral to see why this shows a parameterization. And at the end of the day, you find an answer which is not gauge invariant. That's what I want to emphasize. It depends on Q. And that is fine because if you did the calculation in the other case and were careful with your C dependence, you will find the exact same term. Your normalization condition will take care of your normalization condition will make sure that everything will cancel. We set what is the normalization condition here? So from this integral, we want to set this guy to the value of this guy at arbitrary low energies, right? When this guy goes to 0. What should that be? That should be minus IE gamma mu, but now this is E renormalized. This should be the coupling of QED, right? So that's not the way when you do these integrals, as you saw, what naturally comes up is this parameterization, right? This is the alpha of QED. The idea is the following. We've measured this. We've measured the strength of coupling of electron and photon deep in the infrared. This is a dimensionless quantity, right? What is that number? It's 1 over 137. Something we've observed. It's an important number in nature. And we could use this to normalize QED. Now, here's an important statement. It comes out to be 1 over 137. That's good because it's a small number. If it had come out to be 1 over 0.8, or sorry, 1 over 1.5, you could renormalize the theory at one loop, but what you would calculate would have large corrections. So you would have to work way harder. This justifies the fact that in low energy, this is just a nice fact about nature, right? That alpha QED, the coupling of the photon and electron, is very, very weak in low energies. So that's good. You could do perturbation theory, normalize at one loop, and you know that because as you go to higher orders, the next order, if something is order alpha, the next order is going to be at least 1 order of alpha higher. Why is that? Because if you're adding a loop, it requires at least 2 vertices, right? So every order that you go up adds 2 extra zeros. So that's good. That's a reasonable perturbation theory. Now, you're not always this lucky. There are particles in Sano model. There are theories where the coupling is not very small, That just means that yes, you can normalize the theory, you could do perturbation theory, but good luck. It's painful. So those theories, when I said that EFTs are just fine for say non-renormalizable theories, as effective field theory, that's true if the coupling is small. Otherwise, it's a useless theory. Good. Right, so I'm gonna skip all of this stuff. Okay. I went over this way too fast, but because I want to get to the end of the renormalization of QED. But here's what you observe. We renormalize F1. So here, let me just go back. What did we do? We calculate this diagram. We at Q going to 0, we use it to normalize our theory. Now we could go and calculate what this diagram, the value of this diagram is when there is a photon that's being emitted at some value of Q not equal to 0. Right? So that would involve, now this is a physical calculation we're doing. That would involve subtracting F1 of Q squared from F1 of 0. Right? If you just do that, here's the expression you get. Now, there is some trouble here. This term, this is divergent in the z going to 1 limit. I absolutely encourage you guys to do the calculation step by step, find this term, and see that it is a fact that this is divergent as z goes to 1. This is not a UV divergence. When we talked about dimension counting and everything, we were talking about ultraviolet divergence. We were talking about integrals blowing up because the loop momentum was getting large. Here, something is blowing up because there is a parameter that could go to 0, that could be arbitrarily low energy. They can also give divergences. These are called infrared divergences. A renormalized perturbation theory only guarantees that there are no UV the UV divergences are going to be subtracted, but there could be IR divergences. This is a serious physical issue. Now, I'm going to invite you to think about what it's saying. What could be the resolution? We've done some integral, we took care of everything, the UV divergence is canceled, we normalized our theories. What we're finding is that the processes that we have, they blow up for emitting arbitrary low energy photons. You're a physicist in early days of early 20th century, and you're faced with that issue. Like you've heard about divergence in QFT, the UV divergence pushed to under drug, renormalize the theory. This is an infrared divergence. What would be a thought? How would you take care of this? Think about you are trying to use quantum field theory as a predictive, as a machine that predicts stuff. So what is happening is that there is an integral that you're taking over something, over some photon propagating, and the photons that have arbitrary low energy contribute to an infinite amount. How would you fix that?
Try arguing that they can't have arbitrary energies. They're quantized to some.
That would be a theoretical approach, but be motivated. Like, think about experiments. What is it that you're trying to calculate at the end of the day? At arbitrary high energies, you say, well, I don't have that much energy to detect it. That's the motivation behind it. Arbitrary low energies, are your detectors sensitive enough to detect arbitrary low energy photons? No. Every like the frequency, the wavelength of the photon, if it's something, you need a device of that order to detect it. So realistically, in quantum field theory, what you're interested in You have a physical question. I want to know a process, and this is the range of photon masses that I can observe, right? If you take that into account, quantum field theory forms of charge. However, theoretically, there's an issue of infrared divergences. QED. Now we could get into this is still a topic of okay. QED doesn't have a problem. I have not explained it to you guys. There's a beautiful cancellation that happens magically. Things work out nicely. You can read Peskin about that. But the issue of infrared divergence in quantum field theory is correct. Is important. It's there. There are infrared divergences in quantum field theory, and the usual answer to that is physically relevant questions involve photon detectors that are sensitive to photons of minimum energy. So we cannot distinguish between this phenomenon, this scattering, and this scattering with some photon arbitrarily low energy. Photons that are very, very soft, low energy, very, very low energy, we call them soft photons. We cannot distinguish between them. So these are called Bremsstrahlung law. This phenomenon of emitting arbitrary low energy photons is called Bremsstrahlung. If you ask for the total cross-section with soft photons below the detector, the cutoff, the divergences cancel exactly. This is the so-called soft photon theorem. So in other words, a finite detector efficiency, a detector with finite resolution, will provide a physical infrared cutoff for the theory. It's a physical infrared cutoff. You might still worry about the Hilbert space of QED or like non-abelian gauge theory. What does it mean that there are these infrared divergences? That's something we worry about. It's a topic of active area of research. However, as an experimentalist, quantum field theory is just perfectly fine, right? This is the issue of infrared divergences. They're of very, very different nature than UV divergences. What is the origin of it? Massless particles. This happens with photons because a photon there's no mass. So, the propagate is 1/q squared plus I epsilon, right? But when a particle has a mass, that mass is an infrared cutoff. Below that mass, the photon is not produced. The particle is not produced, right? So massless particles often are intimately tied to this. And then we're going to learn very soon that masslessness is always related to a symmetry. We're going to see that at some point in this course. All right. Any questions about this? This is probably all I'm going to say about infrared divergences. I know it's very, very short, but quantum field theory is a lot to say. Any questions? You have a question?
I'm not sure.
Okay, just ask.
Well, you mentioned symmetry right there. Is that have to do with like spontaneous symmetry?
Very, very beautiful. Yes, we're gonna see that. Every time you have spontaneous symmetry breaking, you end up with the so-called boson mode. They must be massless. Photon is massless because it's a boson. Yes. So it's a consequence of symmetry. There's a very simple. Well, I have not taught a renormalization group, but let me just say it in words. If you have a mass, the question comes up: mass at what scale? Right? Because it could change. Now, mass is this term in the Lagrangian, m squared, phi squared. This is a coupling. What's this dimensionality? It has positive dimensionality, mass dimension, which means it's a relevant operator. As you go to lower and lower energies, the mass grows. So if you see a particle that's very, very light, this requires that at high energies, the mass has to be absurdly small. As you go to higher and higher energies, if let's say there's I detect a particle that has a tiny mass now, right? at this scale. It means that deep in the UV, it had to be almost zero with like 0.000000001. That is fine tuning. That's not natural. So we don't expect things that could be massive to have lower masses, unless there's a symmetry that protects, that says there cannot be a mass term. We saw that in the case of photon, right? The pole of the photon could not be shifted. Ward identities made sure there's no such a term. All right. Renormalization at higher loops. At higher loops, one of the phenomena that could happen is that diagrams can contain divergent subdiagrams, right? For example, you could have a diagram like this, and then the hope would be that, well, this diagram will cancel it. It turns out that it's not given, but people prove this. There's a beautiful theorem called the BPHZ theorem that proves that in using local counter terms, we can capture all the divergences of this form, all the divergences of higher loops. This took a lot of hard work to prove, but you could be happy about it now. It's proven. You don't need to know what the proof is. I don't know the proof either. So let's give an example, the structure of it. Actually, yeah, let's go. For example, consider this is a two-loop correction to the vacuum polarization. As K2, so there's a K1 loop, and then there's a K2 loop here. As K2 goes to infinity, roughly speaking, this phenomenon, well, okay. This is the diagram. This is the diagram, the thing that takes care of it, right? I was gonna, yeah, I'm not gonna say it that way. Yeah, but roughly speaking, the sub-diagram that's divergent, you crop, like remove that sub-diagram and replace it with the corresponding counter term. For example, there is maybe I should say. So, for example, what is this diagram? Which counter term should cancel this diagram? You could think of it this way. You could try to shrink this guy to a point and just put a counter term for that, right? So what is this? You would shrink this guy to a point and you would put this, right? So what happens is that if you're trying to calculate this diagram, it has a sub-diagram of this type, this form. Actually, I'm not going to comment on the counting of dimension counting, but this, let me write it. So I'm drawing the 1pi actually. 1pi. So the 1pi would involve this, right? So what happens is, what are the counter terms for that? Oops, sorry. There's this. There's this. And then there is this. This is the counter term coming from the fermion mass, right? So this is delta 2 here, right? This, what do we call it? Whatever we call it, delta 3, I think we call this one. And then this we call delta 1. So what happens is that as we go to higher order in perturbation theory, the cancellation of divergences requires some magic between these different counter terms. Before, what happened at one loop was that, well, for each of these diagrams that we saw 3 diagrams and we had 3 variables, so it was just kind of nice that we could just cancel them out and it all worked out. But as you go to higher order in perturbation theory, it's not guaranteed. So this theorem is very, very nice. And the theorem relies on the fact that the theory is renormalizable, right? If the theory were not renormalizable, what would have happened is that clearly as we go to higher order, we would have struggled. We would have needed more and more counterterms. All right, so this is the end of this lecture. I went through a lot. I understand that I jumped over a whole bunch of steps. The goal is this. We're going to come back to, we're going to redo all of this in more detail for non-abelian gauge theory, right? But I absolutely invite you to do this. I'm just going to try to include as a homework problem that I know it's going to be super lengthy, but it's sort of absolutely essential. There are 3 diagrams that you were used to renormalize QED at one loop. You know all the tricks. You should be able to do every single integral one by one, see the cancellations of epsilon, MS bar scheme, keep track of the gamma dependence, and see how it works in action, right? I just basically gave you the answer very, very quickly, but you should be able to. So that the homework for part 1 of this section 1 of this course will be actually going through all those calculations, and so that you can actually see what I'm talking about here. Good. Any questions? A lot of this will start making more sense once we talk about renormalization group. At this point, it still seems like some crazy magic going on. Not. Thanks so much, guys. Is it better? Do you guys prefer if I just did not record and do slides and did on the chalkboard? Because you're all showing up. I think no one else is online. I can just do chalkboard. Recordings are good.
Yeah.
Okay.
Just something.
Okay. Well, that's fine.